For almost 100 years, audio recording hardware and mixing consoles have been used to process music and speech to preserve them for our children. But it's annoying when modern hardware doesn't do what it's supposed to. With older hardware, it was common to include a circuit diagram, which is probably rarely found today. In the case of a defect, the only option is an RMA, if you still have warranty, or a repair with costs. Especially when it comes to digital hardware, it gets expensive because you often just replace whole boards. Today I want to show you what you can do with a little hardware effort and a little technical understanding if you have a digital audio hardware that no longer works completely. These devices are rarely completely defective. Before we get started, here's a quick look at the typical signal path of an analog audio mixer. The input signal is usually fed to a preamplifier and then to a multiband equalizer. If necessary, a few aux paths can be added afterwards. At the bottom is the fader for the channel volume. From these individual channels it then goes to the main section, from which it then goes to the PA or recording or anywhere else. Modern digital mixing consoles often work on this principle as well, even though digital signal processing, or DSP, makes signal routing much easier. Digital technology has also meant that instead of using many individual wires in a multicore, we can often transport multiple signals in a single Cat5 cable, means audio over Ethernet. And that's exactly the kind of signal we'll be looking at today. I recently purchased this unit here. It's the P16-I from Behringer, and it has 16 individual analog inputs at the back, going to 6 digital Cat5 outputs on the front. The protocol used here is a proprietary 16-channel audio over Ethernet protocol called Ultranet, which is a layer 1 protocol because it uses Ethernet hardware but no Ethernet packets, which is good and bad. The good, we are not fighting against other network packages and the audio is always at top priority. The bad, we cannot decode the audio samples with a computer directly. If we connect some hardware that is actually intended for this purpose, like this P16M, we see that this piece of hardware does not work as expected. As you can see, my P16I recognizes the P16M, but the Ultranet LED is not on, so there's no digital communication between this device and my P16I. The power is okay, but no data is exchanged. As an electrical engineer, there's only one thing left to do. Let's open it up. To get a better overview, let's list the individual ICs and take a look at the basic connections. Directly at the jack connections, we find the analog-digital converters for the audio signal. These are connected here to an FPGA, which then passes the processed signals to 3 octal buffer ICs. These are then connected again to the 6 Cat5 connectors on the front. The many additional cables connect the input level selector switches and the LEDs. If we look at the datasheet of the octal buffer IC, we see that we have 8 inputs and 8 outputs. And here it seems that we are simply matching the levels of the FPGA to the levels of the output signals. So let's connect an oscilloscope to check the signals. Okay, the LED on the front is not lit either. Probably the FPGA disables the signals if no connected device is detected. So we connect the P16M again. Ah, much better now. Okay, what is that signal now? Let's try to find a pattern. There we have a pattern. Apparently, the signal repeats every few microseconds. With a little web search, the website of Clark Technique, a subsidiary of Music Tribe Holding, which also owns Behringer, reveals that Ultranet apparently transmits 16 independent 24-bit signals at 48 kHz. If you look on the internet for different digital signals, you will find the digital structures of SPDIF, AES-EBU and ADAT. Let's take a closer look at the app note for the commonly used AES-3 or AES-EBU. It is therefore a digital signal with up to 24-bit and a sample rate of up to 192 kHz. The signal is also biphase marked encoded and has a quite simple structure. 20-bit audio data plus 4-bit auxiliary bits, 4 status bits and a synchronization signal. Let's calculate the distance between two sync signals. Yeah, this corresponds to 384 kHz, but 384 kHz divided by 48 kHz are only 8 channels. Where are the other 8 channels? Let's have a look on the Ethernet standard as we are using layer 1 Ethernet here. Twisted pairs of wires are available for Ethernet. Ultranet uses pins 1 and 2 for 8 channels and pins 3 and 6 for the other 8 channels. The other pins are intended for the power supply so that a connected P16M, like here, can be supplied directly, for example. So we have sufficient evidence that we are dealing with two AES-EBU signals with 8 channels and 48 kHz sample rate. Now that we have access to these serial signals, we can make more of them. In my last YouTube video I had already introduced this Arduino here, the MKR Vidor 4000. We simply use this mix of microcontroller and FPGA to build a simple digital audio mixer with 16 channels out of it. So first we need to make a hardware connection between this half-defective P16-I here and our Arduino. Both obviously operate at 3.3 volt level, which allows us to easily make a connection directly. Since we are not using differential signals on the Arduino, I simply connect the TX Plus, which is on pin A1, A3, A5 or A7 of this octal buffer I see here. Presumably the design uses A1 and A5 for channels 1 to 8, of the P16-I and A3 and A7 for channels 9 to 16. We'll find this out later. Let's start Quartus Prime and add some VHDL blocks to the project. Since AES-EBU is not an unknown format, we can simply use a ready-made AES-EBU decoder from opencourse.org. This logic recovers the audio clock from the biphase marked encoded signal and provides the audio signal as a standardized I2S signal. I2S was designed many years ago by Philips for communication between audio ICs. Again, we use a ready-made block from opencourse.org that can receive I2S data and output it as a bit vector. We only have to add a channel counter, which sets the counter to 0 each time a Z preamble is reached and is incremented when an X or Y preamble is reached. Finally, we will reset the counter to 0 when we are above 7, as we expect only 8 audio channels on one transmission line. As soon as new audio data is now present in the vector, a control signal is set to high, which is distributed to 8 individual 24-bit vectors by a downstream buffer block. From now on, we can do everything imaginable with these simple audio samples. The most obvious thing would be a test output to an analog system. But how can we get the purely digital FPGA to output analog signals? Thanks to standardizations, we do not need to do much different than when receiving the audio data. We simply use AES-EBU again and output a stereo signal on a standard converter like this device here. According to the specification, an RF transformer should be used, but a direct connection between the Arduino and these coax input here should be fine for testing. We simply apply 2 of the 24-bit vectors to the input of an SPDIF transmitter, which is nothing more than a logic block that uses a fixed sample rate, our 48 kHz, to convert all 24 audio bits into an AES-EBU format with biphase mark encoding, and then outputs this signal to a digital pin. For everything to work properly, we still need to provide the individual logic blocks with a suitable clock. The input blocks must be clocked with a considerably higher clock rate so that the bit edges of the digital signals to be read can be detected reliably. The microcontroller gives us 48 MHz as a base clock, which we can rise up to 100 MHz or more via a so-called phase lock loop, or PLL. We only have to distribute this HF clock to the individual receive blocks. Only the SPDIF output needs a much lower clock rate because the single bits are clocked directly with it. At 48 kHz sample rate and 24 audio bits plus the additional 8 bits for the header and the factor of 2 overhead for the biphase marked encoding, we need a clock of 6.144 MHz here. Then I'm curious if you hear anything. So let's plug in this plug to the connector. Okay, we have some sound here. The LED is blinking, but as you can hear, we have some noises there. So let's find out what is the problem here. So maybe we can increase the clock rate a bit and use 200 MHz instead of 100. Sounds much better now with 200 MHz clock rate. Maybe the edges of the bits have to be detected a bit better. Now that we can decode the Ultranet signal and bring it back to the analog world, everything is open to us. The basic functions of an audio mixer are volume control and left-right panning. With a microcontroller on the Arduino board, we also have an USB connection to a computer. But first let's look at the FPGA side again. For volume control, all we need to do is multiply by a factor between 0 and 1, meaning 0% and 100% volume. Unlike microcontrollers, however, the handling of fractions of a number is a bit more complicated. Therefore, we limit ourselves to a multiplication with a value between 0 and 256, or full 8-bit, and divide the signal by constant 256 by a bit shift of 8 bits to the right. Thus, we can perform the entire calculation with integer values. So we create a logic block that provides an audio sample and single multiplication values, each for left and right. Here we can also provide further values, for example, for auxiliary paths. On the output, we now have separated audio samples for left and right. Our audio engine is now almost ready. The only thing missing is the connection to the computer. The onboard SAM-D21 controller is connected to the FPGA via a UART connection. Therefore, we implement a simple UART receiver and a simple protocol. My protocol has 9 bytes, of which the first and last bytes define the start and end with the character A and E. 2 bytes are used for a 16-bit error check, which is simply the sum of all payload bytes. As payload, we have a command byte and a 30-bit payload part, which contains our volume information. On the Arduino side, we now just need to implement the counterpart for this protocol and provide another protocol to communicate with the computer. Here we simply use an ASCII-based communication so that we can easily control our new audio mixer via a terminal. After initializing the 2 serial ports, we can test our system now. Okay. 100% is working, 0%, Working too. 50%. Yeah, this is not working at all. 75%. No, not really. 85, 95. It's getting better. 97. Even more close. Okay. At 100% it's working. At 50, only disturbances. So what is going wrong here? Now, in the calculation, we have to pay attention to the fact that we are dealing with pulse-coded modulation, or PCM audio, with signed integer samples, and thus the most significant bit is the sign bit. Up to now, we have ignored this in the multiplication. We are just multiplying bit vectors. But by adjusting the volume block, this is quickly corrected. So we have to change our standard logic vector to a signed input. And then we have to change the multiplication from unsigned multiplication to a signed one. So 100% working, 0% and 50%. And in between, so let's test 75, 25, 15. Well done. Now it's working. Now we have almost all the functions of a simple audio mixer. The only thing missing is the sum of the individual channels and the main section. The sum of the 32 audio samples, 16 for left and 16 for the right, is exactly that, a simple addition of the individual signals. The only restriction here is that we can easily slip into a signal clipping if the signals to be summed are at quite high levels. This could be solved by signal processing with floating or fixed point signal, but this is again more complex in the FPGA. After the summing block, we add another multiplication to realize the main fader section, and the resulting output signals are already the audio samples that we can send to the SPDIF output. Well, after tidying up the project a bit, we have the receiver for 2 Ultranet streams with each 8 channels of digital audio. Afterwards, the audio mixing section with the volume control and left-right control. The sum section here, where we can summarize all 8 to 16 channels for left and right, so we have 32 channels. And at the end we have the main volume section for left and right. And afterwards we are putting it to a SPDIF controller. The audio mixer can do almost everything now. Receive audio data, mix it and output it to a SPDIF signal. But as a DIY project, you can even realize the analog audio output yourself. For this we need a little excursion into other parts of electronics. LEDs. They are known to use PWM or pulse width modulation for brightness control. With a fixed switching frequency, the width of a pulse changes, but this does not work so well with audio signals. Here the use of a PDM or a Pulse-Density-Modulation is more suitable. This is a method that is used in many sigma-delta digital audio converters or even cheap MEMS microphones. We already have the audio samples as bit vectors, and now we only have to output this vector with a suitable sample rate as PDM stream on a digital output of the FPGA. From this table we can read the required PDM clock. Since we have audio data with 48 kHz bandwidth, we naturally want to use this bandwidth at the output too. So we have to use a clock of 4.8 MHz with a decimation ratio of 50. Now we only have to connect a low-pass filter with around 48 kHz cutoff frequency to this FPGA pin and feed it to an audio amplifier. A frequency of 48 kHz and a resistor of 10 kΩ result in a capacitance of 330 picofarad. All we have to do is constructing this kind of low-pass filter. The music is already playing and now I'm connecting the cinch connector. And it seems to work. Hey, it's fine. We are only outputting with a digital output to a low-pass filter and we have clean audio output from our FPGA. For a better handling, I've created a small PCB with an Ethernet connector and a buffer IC. It can be used to connect a fully functional device with Ultranet to the Arduino much easier than soldering cables to the ICs directly. This PCB can be found on GitHub, but it is not tested yet well and might have some issues. First of all, I will repair my P16-I to have working Ultranet connectors again, then I will test this PCB in detail. So with this, we now have access to all sorts of possible digital audio sources. So you can build an audio mixer for different digital sources with this hardware or convert between different sample rates. In addition, one can transfer data to the microcontroller via the I2S interface and then, for example, transmit it as a live stream to the host computer or save the data to an SD card connected to the SAMD21 controller. The possibilities are unlimited. You can find the whole project on GitHub, so you can experiment with the hardware yourself or add more functions. Your ideas are very welcome. Well, that's it for today. Have fun tinkering with electronics and see you next time.